All right, let's try this problem. Here they tell us that 10 grams of steam at 100 degrees Celsius is bubbled into 150 grams of cold water at 20 degrees Celsius in an insulated container. They'd like us to determine the final temperature of this mixture, and they give us some helpful information, including the heat of vaporization of water and the specific heat capacity of water. All right, let's start by analyzing the problem. What do we have here? We have something hot, steam, hitting something cold, the cold water. So we have hot that meets cold with no reaction. This is just a heat transfer. Whenever we have a heat transfer, start with heat lost is negative heat gained. So let's go ahead and write that down first. Q, that's lost, equals negative Q, that's gained. Okay, now, what is losing heat? What's losing heat is our steam. What's gaining heat is our cold water. Okay, now that's the basics. We just need to analyze where's the gain happening, where's the loss happening, and how. So let's start off by looking at our steam. Our steam starts off in the gaseous form, and then it hits the water and it cools down to some temperature below 100. So we're talking about a phase change plus a temperature change, both of those. Let's look at the heating curve and how this applies. So if I were to draw a sketch of water's heating curve, on our y-axis, we would go ahead and plot temperature, and on the x-axis, we would show heat added. And typically for water, it looks like something like this. We start off at the solid state, increase in temperature. Then once we hit 0 degrees, we get a plateau for our first phase change, melting. And then liquid water will rise in temperature until it reaches 100 degrees Celsius. At that point, we can go ahead and boil water, and then it becomes gaseous steam that can rise in temperature. So here's where we're at. We have steam, the gaseous form right here, but it's at its boiling point, its vaporization point. So we start right here. Now the steam is going to hit the water, and that steam is going to condense, do a phase change, and then it's going to cool down to come to some final temperature above the temperature where the water started, 20 degrees, but less than the 100 degrees that it started at. So that is what our steam has to do, a phase change and a temperature change. So the heat lost by the steam, we're going to have two parts. Let's start with the phase change. We need to use the heat of vaporization, which is given as 2,260 joules per gram. So to get the joules out of that, we just need to multiply by the mass, the number of grams of steam that we have. So we're going to have a mass of our steam times that heat of vaporization during the condensation process. Plus, we have another factor for the steam. Once we go through the phase change, we have a temperature change. So then we're going to go ahead and do the MCAT, the temperature change for the steam. Okay, that takes care of the steam. What about the water? The water starts at 20 degrees and is just going to rise but not get to 100. So we're just doing a temperature change for our water in this case. So we want to do an MCAT, but we can't forget the negative sign over here. Heat lost is negative heat gained, and the heat gained is MCAT, and that will be for our liquid water. Now we get to go ahead and plug in our values. So we're going to start with the mass of the steam. We started off with 10 grams of steam, 10.0, times the heat of vaporization of steam is our 2,260, but this is going to be the biggest mistake students make. Since we are condensing, not vaporizing, vaporizing is an endothermic process that requires energy. Condensation releases energy. We don't want to use a positive 2,260. Instead, we need to use a negative 2,260 joules for every gram. That's the biggest mistake, releasing heat. Positive in this direction on the x-axis, negative in the other direction. So now we're going to plug in the mass of the steam again as it cools as a liquid, 10 grams. We're going to be in the liquid phase once it starts to cool down, so we get to use the specific heat capacity of water, 4.184, and the temperature change of our steam is going to be T final minus, well, it starts off in its liquid phase at 100 before it starts to cool. So T final minus 100. Okay, that takes care of our steam. This equals negative mass of our cold water that will begin to rise from 20 degrees. That cold water started off as 150 grams. The specific heat capacity of the cold water, 4.184, and then T final minus the initial temperature of the cold water was 20.0 degrees Celsius. All right, it's just algebra from here, folks. So we've got 10 times 2,260. That is a negative 22600. Now we have 10 times 4.184. Well, that's 41.84 times T final. So we're going to add 41.84 T final minus 10 times 4.184 is 41.84 times 100. So we're going to get 4,184 when we distribute that into our factor right here. This equals negative, we've got 150 times 4.184. That is negative 627.6, and then we still have TF minus 20. Okay, so we've got negative 22600 plus 41.84 T final minus 4184 equals, I'm going to go ahead and distribute here, negative 627.6 T final, and then a negative times a negative is a positive 12552. All right, we're going to gather like terms. I'm going to bring my final temperatures over on this side of the equation and then everything without a final temperature over on this side. And if we do that, I got 669.44 T final equals 39,336. Almost there. Last step. We're going to divide by 669.44. And if I do that, I get a final temperature of this mixture of 58.8 degrees Celsius. And then we think about our answer. We had water that started off at 20 and steam that started off at 100. We meet somewhere in between those values, and 58.8 is definitely in between those values. I hope that helps. Take care.